Hi, I'm Kelvin, a principal engineer at Snowflake. We at Snowflake recently released Arctic, a top-tier enterprise large language model that pushed the frontier of cost-effective training and openness. To continue with the openness, we would love you to share some of the detail of how we use Snowflake data platform to prepare training data to build an efficient, intelligent enterprise LLM. Training LLM such as Arctic takes a lot of data. The data can come in many different types. For example, there can be public data sets such as Hugging Face and Common Crawl. Or you can bring your own private data set as well. This data set usually come in many different file formats. Some of the data set is also very huge, as you can see in the green Common Crawl box. Each of the Common Crawl usually is tens of terabytes, and there's almost more than 100 of Common Crawl snapshots. So we are talking about petabyte of information here. It's not sufficient just to collect all this data and fit into training your LLMs. The other important aspect of building a good LLM is to have very good data qualities. There are many strategies of filtering out low quality tokens to improve your training your models. So I have done this type of work at previous company, both at search startup, Niva, and at Google. What you put into the model is what you get out. The higher quality of to improve the data, the better the models becomes. Traditionally, one write a lot of custom code and data processing pipeline to work to prepare the data into LM trainings. As an example, there are many open source data set or frameworks such as Web Pajamas. They usually come with a data set with signals such that you can filter low web quality tokens to increase the quality of your LMs. Alternatively, you can also work with a web crawl like a common crawl yourself and use distributed processing framework such as Dask or Spark to do custom processing pipeline. Usually, once the data process is done, you usually write this data into S3 in AWS or other file-like object in the cloud. The post-processed data is then used in training large language models. As an engineer at Snowflake, we took a very different approach. What we do instead is to natively do this within Snowflake to prepare the training data for Arctic. So one may ask, why does it make sense to do all this data preparation work in Snowflake? Many people know Snowflake for their cloud-based data warehouse. They are very good at doing distributed data analysis on very large data set. It also has very powerful government and data lineage capability out of the box. However, usually ML data engineer don't associate Snowflake with LLMs. However, with combination of capability of the thing that I just mentioned, actually is ideal for data processing for LLMs. In today's talk, we will demonstrate how we can use Snowflake to process large volume of data efficiently, besides the efficiency that I just talked about. Doing an LLM's data processing on Snowflake also gives you additional benefit, which include provenance, data lineage, as well as policy enforcement on your data. So once the data is in Snowflake, it also unlocks fast iteration of your data, which is critical to build a very good LLMs. We have built tools on top of Snowflake using Streamlit to help us iterate data quality within hours. In this talk, we will show you some of those tools and how it helps us to enable fast iteration loop within Snowflake. Here is the agenda for today. Nathan will first walk us through a data creation process with a practical case study of building this data sets over code. He will demonstrate how you can prepare this data efficiently, provide provenance data lineage, as well as enable policy enforcement. I will also talk about some of the tooling to enable rapid experimentation to improve our data quality on top of Snowflake, which is critical of improving LLM model qualities. Now I will pass to Nathan. He will deep dive into practical case study on building data set over code.
Hi, I'm Nathan Wiegand, a principal engineer working on Arctic. Today, we're going to build a dataset over code as an example of how we manage training data for Arctic. In order to train the best possible LLM, you need to source the right data, you need to clean and process that data, and you need to have the right model architecture for efficient use of that data. Today, we'll focus on the data processing part of that story, specifically how we curated our code dataset. There are many sources of code datasets online, for example, at Hugging Face. Let's just focus on how you prepare your dataset after you've acquired it. When building our dataset, we want to make sure that our data is of highest quality. We start by loading the data into Snowflake. At first glance, you might think of a code dataset as being a table with 3 columns: repository name, file name and path, and the file contents. But we observed that about 20% of the file contents are actually duplicated into at least 2 files. So instead, we break the table into 2: file metadata and file contents. This saves a lot of storage costs, and it makes some queries a little cheaper. Also, structuring the data this way makes it really easy for us to do file-level deduplication because we've already computed the content hashes of all of the files. On the left, we have the file metadata table, which is keyed by repo name and path and has a column called the content hash. On the right, we have our file contents table. It is keyed by content hash and has a column called contents. The thing to note about the table on the right is that each row occurs exactly one time. It is globally unique across content hashes. Now that we've loaded the data, let's talk about data cleaning. While there are many aspects to data cleaning, I'll cover 2 here today: file level annotation and repo level deduplication. Since the end of the day, these code files become examples as we train our LLM. Our goal is to annotate the files with quality annotations that we can use for further processing downstream. For each signal, rather than computing it more than once, we want to permanently associate it with the file in the file metadata table. This makes things more efficient. The Big Code project suggests several data cleaning attributes in their paper, Star Coder, May the Source Be With You. Let's cover how we built 2 here. First, let's build a signal called isNoisyXML. There are many files in our data set that are machine generated or that use complex XML schemas as storage format. We might find these to be less interesting for our LLM. So what we'll do instead is we will annotate these XML files and say that they're noisy if they are not XSLT files. XSLT is a programming language that happens to be stored in XML. Here we create a simple new column on our file metadata table called isNoisyXML. Let's read the query that populates it from the inside out. First, we process the file contents table to find all code that appears to be XML files. These are files that begin with a special marker, which is $XML. We could be more defensive about whitespace or capitalization, but for this example, we'll just use the starts with function. This now returns a list of all content hashes of files that we believe are XML files. We update our file metadata table's new isNoisyXML column when the content hash matches the one in our set, but where the file does not have an XSLT file extension. Here, in just a few lines of SQL, we were able to populate a new document annotation that combines concepts across 2 tables. While the last example was very simple, let's do something way more complex. Let's add a new attribute, which is about detecting whether or not a file is noisy HTML. We'll say that a noisy HTML file is one that's probably not generated by a person. So that's an HTML file where fewer than 20% of the characters in the file after rendering are still visible. Now, doing this in SQL would be very, very difficult. So instead, it would be really great if we could rely on one of our familiar Python libraries like Beautiful Soup. And we could do just that. Snowflake supports running Python scripts along with Java, JavaScript, and Scala over your data via a mechanism called user-defined functions, or UDFs. Here, we define a new UDF called %HTML UDTF. It takes one parameter, which is the HTML content, and note its return type. It returns a table, and the table has a column which is %HTML visible, which is a floating point number. Here is the body of the function. This is just a Python program. The main thing to note is that we define a class with a single method called process. Process yields new rows in that table that we're outputting. The yielded tuple must match the return table definition above. So when we yield, the first value of that becomes the %HTML visible in the definition. Here, we're yielding the ratio of the length of the rendered text using Beautiful Soup to the length of the original content. If you were to execute the overall query, you would get a new function in your environment. So let's see how you'd use it. Let's assume that we've already created the new column, which is called %HTML visible, and we only need to populate it. Zooming in on the innermost query, we first get a list of all of the HTML files on which we want to apply our content. So that's the innermost filter. By keeping the percentage instead of the label here, we make it easier to do downstream experiments later. So rather than hard coding 20% now, we can see how 30 or 10 affects our actual LLM. As I already mentioned, identifying file quality is necessary, but it's not sufficient to build a good code data set. We also want to investigate repository quality. Many repositories are clones or forks of other ones. And many times, these don't even have meaningful changes. They're just exact duplicates. So we're going to say that two repositories are exactly the same if their file contents are exactly the same. So how we do this is we use the array_ag window function. We just aggregate all of the content hashes of all of the files in the repository. The one difference of that simple aggregation is that we order by the content hashes themselves. This gives us a total ordering over all content hashes in our array. This makes comparing arrays really simple. But we actually don't need the arrays themselves. We just need to compare arrays for equivalence. To make computation easier, let's just consider the hash of the arrays instead. After we've collected all of these hashes of arrays, we'll call them repo hash. Then all we need to do is group all of the repos that share the same repo hash and pick one. For our purpose, any one matters. They're all exactly the same. So let's pick the first one alphabetically. So that's what first value does for us here. The final product of each of these transformations is a new column on our file metadata table. Here's an example of a schema that we might generate. Repository name, path, content hash, these are familiar. We've also added our new isNoisy XML and our %HTML visible. At this point, we've covered how we can efficiently, both computationally and operationally, clean our data set. Now to talk briefly about how we can track data lineage and how we can manage policy enforcement within our data set. We can maintain provenance and data lineage by borrowing an old trick from the database community called database migrations. The first idea is that we never allow an engineer to have write access to the database. This means that you can't add columns or rows or do any mutations whatsoever. Only our production account can do that. Engineers write SQL files, these are our migrations, that say how to mutate the data in the manners that which we've described above. These get then implemented in order in an atomic manner. So at any time, we can guarantee that we know exactly how any column was built by simply looking at the migration files in our Git repository. When we output data for our LLM training, we have a similar problem. How can we be certain that the training data for our LLM was produced in the way we thought it was? For this, we use the same idea. Exports from the database must be done by production jobs that are verifiably built. The exports write to an S3 bucket that only they have write access to. The engineering team can read it all they want. Along with the data, the production job annotates or adds a data card that specifies how the data was generated, by what process, and on what date. With this information, we're able to go all the way from the training data that goes into the LLM for training, all the way back to how exactly it was generated, making the whole system fully reproducible. For code dataset in particular, being able to have certain policy enforcements are a requirement. For example, here, we want to make sure that our code data is appropriately software licensed. For this, we'll use a view. A view is like a named query that we can issue again. In all of our database exports, we will not query file metadata and file contents directly. Instead, we're going to use this view that enforces our policy. This way we can be certain that all data written to S3 is always data that's within policy, and we know how to regenerate it. So far, I've talked about how we implement quality and policy filters on our data, but it's equally important to talk about how we iterate on these quality labels to see exactly which data yields the best downstream result. I'll hand it back over to Kelvin to give examples of how we build tools on top of Snowflake to iterate on data quality.
Thanks, Nathan. That was great. But what I'm going to tell you is even more important than what Nathan just told you. As I said at the beginning of the talk, What you put in the model for learning is what you get out. The high quality of your data, the better the model becomes. So in the next sessions, we'll cover some of those examples of how to build tools to enable rapid experimentation on your data. First, the benefit of having your data in a data warehouse like Snowflake is the ability to query your data. For example, with a simple query, you can ask, what is the top repo in the coding dataset within seconds? In this case, as you can see in the screenshot, FreeCoderCamp is the most popular repo in GitHub. It's very easy to query the data different way to understand the shape and property of your pre-training data. Now we know that FreeCodeCamp is our most popular repository. Why don't we manually invest some of those examples here? This is just a simple /star query. You can see that in the screenshot here. Each of the row here is show the content of the code. This is super helpful to build intuitions on what exactly you are putting into your training your models. In this particular UI, it may not be the best way to quickly browse through your data, given there's quite a lot of other information we are showing in each row. To make browsing even better, we built a simpler Streamlit app. Streamlit is an open source Python library that make it easy to create and share custom web app natively within Snowflake. In these particular examples, we built a simple app with a drop-down menu to select the type of language you want to browse randomly. In this case, we select Python code, and then you can quickly click on the next items to view a bunch of random examples. This is very helpful to build intuition what we are actually have in our data set for training your models. To extend the app a step further, we add 3 buttons: bad, neutral, and good. This allows us to rate the content quickly in one of the 3 categories. This rating is then written back to Snowflake database. This is very important because this enables us systematically evaluate if the dataset is good or bad. Also, once the feedback is written into Snowflake, we can also use it as label to training a classifier to filter out all the bad content. In my past job, our team also built something similar, a human rater tool outside of Snowflake. Just doing a simple rater tool will take up weeks with a small teams. But with Streamlit, I was able to do this in less than 3 hours, even though I'm new to Streamlit. Of course, there's still quite a lot we can do to improve it to a fully functional human rater tool, but this is probably a good start for many people. So a lot of time, you will also want to apply different operation or filtering strategy on your data set to improve the quality of your data. For example, in the StarCoder paper Nathan mentioned earlier, they describe a method for PI filtering on your coding corpuses. I always ask, once I implement those filtering, what is the precision and recall on those changes? How many items did I affect with the filterings? In this particular diff tool we built, we can see that we implement PI filtering in the code and store the content with a PI removed in a different column in Snowflake. In this particular app, you can see the original content on the left and the content PI removed on the right. And there is a diff view at the bottom where it's showing that Kelvin So, the author of the code, is correctly removed and show it in red color. This quickly allows us to go through many examples to see if you are doing the filtering correctly or incorrectly. This helps us to build intuition and also improve our filtering mechanisms. Finally, I would want to show us our eval dashboard. To iterate our data quality, we run hundreds of data ablations to validate if the changes, such as the filtering that we have built, is helping with model qualities. When the experiment is run, we store the eval result within Snowflake. And we also build a simple eval dashboard to help us track progress of our experiment that we run. In this particular screenshot I'm showing here, we ran 4 different data ablation runs. Each ablation run usually gives us many metrics, which you can see on the table on the right. And then we use the average of those metrics to plot a bar graph, which is shown on the left side. This can all be done within Streamlit. So with that, we have seen that we have built a data processing system for Arctic LM within Snowflake. Rather than having to worry about efficient compute, data provenance, data lineage, as well as enable policy for your enforcement on your data. We were able to build all this within Snowflake and leverage Streamlit integration for rapid experiment with different means of improving the data qualities. Looking ahead, our goal is to continue to push on the boundary of what is possible with LM trainings. And then we are already start exploring with different way of generating synthetic data as well as other sophisticated filtering techniques. Now I will pass back to Nathan to give us some teasers on what other thing we have done in Arctic.
Thanks, Kelvin. We've released a series of blog posts detailing how we built Arctic, from data acquisition and composition to how we optimize GPU coordination and training. What we presented today is just a brief overview of how we use the Snowflake data platform to manage our training data for Arctic. Because we were able to iterate quickly and confidently using the tools and techniques that I described, and using the data exploration tools that Kelvin described, we were able to ship a fantastic model tailored for enterprise use cases, going from an empty directory to a shipped model in under 5 months. Please see our cookbook series linked here for in-depth discussion of our model architecture, training infrastructure, data recipes, and much more. Thank you for your time today. We're really excited about the future of LLMs, and we're super grateful for the opportunity to speak with you today.